and share my screen. So yes, welcome everybody to our big data for today. We're going to, last time we talked about our homework assignment, newest homework assignment, this Twitter Postgres indexes assignment. And we're going to finish up the material that you need for this assignment today. In particular, three things that we'll be talking about are, so we made it all the way up to this section right here, full text search in Postgres. We talked a little bit last time as well about full text search in general and some other strategies for that at the end of class. We'll start today with doing this specifically in Postgres. And some of the questions that you're trying to speed up on the assignment are full text search sort of queries. And so this will be relevant for that. And then another part of your assignment is writing queries specifically on the JSONB denormalized data. And so we'll be going over that as well today. And also indexes, which will make both of those two things faster. In order to go over this, I have opened over here two terminal windows. And these terminals are a little bit, I'm set up into two different assignments right now. So this might be slightly confusing. That this top one up here is on the week 12 assignment, the one that is currently due, that we're working on this week. And the reason for that is I'm going to be taking a look at the SQL normalized batch queries, and part of our work today is going to be seeing how to convert these normalized queries into the denormalized queries. Again, our part of your assignment is going to be to actually write these denormalized queries. And so we'll go through the first of the 5 problems today in class about how to complete those. And so that's why the top one up here is in the week 12 folder. The data set for week 12, though, again, is much larger. It's 10 full days of tweets, so 3.1 million tweets. I don't want to be in class building indexes on 3.1 million tweets because that can take, like we talked about last time, potentially up to several hours. And so for this bottom terminal window, I'm in the week 10 folder, the last assignment, which has the much smaller data set, which will let me build the indexes in just seconds instead of hours. And so that'll make things a lot more interactive. When you're working on your homework assignment, this is also a good way to practice writing your queries and writing your creating your indexes, making sure you're good at creating good indexes. You can do all of that work on the smaller data set from last homework assignments. That way you get quick feedback, quick turnaround time on whether your commands work or don't work. And then once you have something that you're pretty confident is going to, or that's working pretty well here, then you can just re-add those commands into your week 12 data sets. Let it spend a couple hours or so creating those indexes for you, come back, run the tests, and see if it actually scaled up to the larger data sets. And in general, that's a really good habit to be in when you're working with large data sets. Always do your testing work, the interactive work that you're doing on smaller data sets, so you get the quick feedback. And then once you think you have something that's going to work well, take it to the larger data sets. So down here on the bottom terminal, I'm going to open up pSQL Docker Compose exec, and I'll be working in the denormalized database today, pSQL like that, hit enter. Okay, now we're ready to get into the technical things, but before we do that, any questions about either what we're doing today, the setup today, anything administrative? Okay, so back over to the notes. again, in this full text search in Postgres section. And the two important data types for text search in Postgres are this TS vector and TS query. The TS here stands for text search in both of these two words. And we're only going to do a really high-level overview of these two types here. So you likely will have to refer to the documentation for parts of the assignment. This is just to get you really quick up to speed with sort of what to be looking for in the documentation. So the first function that we're going to look at is this toTS vector function. And what this function does is it's going to convert a string like this into this TS vector type, which will be used for our actual searches, our actual queries. And these four commands that I have right here, they are not, they don't use any data at all, so we can just type these directly into our database and see what's going to happen. I'll start with these two right here, copying them both over here into this terminal session down here. And both of these call the toTS vector on this string, this is a test. The difference is that up here, this first call has two parameters. The first parameter, when you have two parameters, is the language that you want to use. And the second call down here has only one parameter. When you don't specify the language, it defaults to whatever your system language is, which on the Lambda server is English. So these two commands happen to be the same on the Lambda server. Again, the toTS vector function returns a TS vector type. And what the TS vector type stores is a list of all of the words and their positions in the text. So in this case, up here, this string, this is a test. All of these sort of small words, sometimes called stop words. Stop words are somehow unimportant words because they typically have very short, only for like grammatical purposes. It'd be kind of weird to search for all the documents that contain the word this or that contain the word a. So the TS vector function is only going to keep the words that it thinks that people might want to actually search for, like the word test up here. And all the things that get removed are called stop words. Do another example. This is a test of Postgres's FTS system like that. I'll hit enter. So it was still in a comment, maybe. Yes, what's happening is I use the single quotation for possessive right here, and that's breaking the string right here. I need to escape that. And in Postgres, SQL in general, in order to escape a quotation mark inside of a string, you double up the quotation marks like this. And so let's see a little bit more about, there's these four words down in here, things like of got removed. FTS, not a real word, just an abbreviation. It still knows to keep that around though. Interesting thing here is this Postgres with an apostrophe. Part of this toTS vector function, it does what's sometimes called stemming and lemmatization, which is the process of converting a word down into somehow a simpler form. And so like searching for Postgres' apostrophe S, people are unlikely to care about this apostrophe S part. And so it takes that away and just stores postgr right here. It also takes off the S over here because it thinks that that's a plural word. So like, let's say I have system, change that to systems, plural, tests, plural, like this. hit enter, and you see we get the same results down here. It's going to like be normalizing all of these words for us down to some sort of standard form. English, there's not too many sort of like different conjugations of different words. Less than 10 forms for any given word. With other languages, like Spanish, more than 200 conjugations for different verbs in Spanish. And so this normalization or stemming and lemmatization process is important for that. So yeah, that's again with the English language right here. Postgres is somehow using its knowledge of English in order to do that. If we change this from English to simple, then that disables all of the stop word removal and the lemmatization. So the simple language disables lemmatization, stemming, and stop word removal. So now you can see that like tests here is plural, and then it has all of these smaller words like this. So if you really wanted to capture all of those things, that's what you would do, keeping the word simple over here. Anytime, so where this is used in practice in full text search is that anytime you are representing a document in order to do the search with it, you're representing that document as a TS vector. So anytime you are searching in a document in Postgres, you represent the document as a TS vector. The other important type, well, let's see, sorry, so that brought us up to here in this example. The last thing right here, if we do the : TS vector, that's the same as using the simple. So directly casting like this is the same as using the simple language. So again, the double colon right here, coming from the math notation of specifying a type of a value, says the thing on the left gets cast to the thing on the right. And so that's our results. In order to do an actual query in Postgres of doing the full text search, so here we have if we had a text column inside of tweets, which the normalized database does, then this is how you do the full text search right here. So TS vector, again, converting the language into English. This is the column right here that we're doing the full text search on. And then we use this double @ sign right here. The thing to the left of the double @ sign is the TS vector, and the thing to the right is this TS query. TS query, again, the language, and then the search terms that you're using over here. This TS query function supports a pretty general syntax for doing complicated queries, like if you were searching for United States, making sure that the word United and States are right next to each other, or other things like that. But we're not going to cover that syntax in detail. The important thing here is that this double @ operator is what's used to do the full text search, and the thing to the left must be a TS vector, and the thing to the right must be a TS query. Any questions about the full text search so far? Okay, we'll see some more examples of this with our actual Twitter data set here in a second. In order to do that, we're going to talk a little bit about the gem and rum indexes. But in order to talk about these indexes, we're going to talk about the JSON operations first. So here's just a quick summary of creating these indexes that you can reference back to after we talk about them. We're going to jump over to the JSON operations next. Again, these JSON operations are for the way they'll come up in your assignment is you'll have to write queries on the denormalized database using these operations. And there's many different operators and functions for working with JSON. If you click the link right here, that'll take you to this page, and you can see there's just hundreds and hundreds of functions listed down here. You don't need to know all of them. These are the 5 that sort of I regularly use, and the ones that you should be thinking about when you're working on the homework assignment. So the first one, JSONB Pretty, is for debugging, giving you pretty printing of your outputs. So again, in this database, the denormalized database, the tweets_JSONB is where the information is stored. Let's do \d tweets_JSONB. See, that has only this one column, the data column of the JSONB type, which is directly storing the information from the zip files. And if we do a select JSONB Pretty of data from tweets_JSONB like this, this is going to pretty print all of these columns just so that we can remind ourselves what the format of the JSON files is like. Before we actually run this though, I just want to remind ourselves how many points we have in this data set. So 100,000 here in our smaller week 10 data set, the Twitter Postgres parallel assignment, again here on the bottom, last programming assignment. So when we're doing this, running the JSONB Pretty function on the data, we don't want to do that on all 10,000 of these tweets probably. So I'm just going to add a limit 1 right here so that we can see just the first one of these JSON files, JSON entries, and things will be faster and not as confusing that way. And here's what the information looks like. What we're going to do is, let's see, we want to find the screen name, the username of the person who sent this first tweet, and the text of this tweet. So the screen name right here, screen name key inside of the user entry of this JSON object, and then the text up here just directly in the JSON object. So in order to get information out of these JSON types, well, let's see, let's first just see what happens if we select the JSON type like this. You'll see that it's this sort of like very hard to read blob of stuff. So very rarely what you would want to do, very rarely will you just directly select the JSONB type from a table. Instead, these 2 operators here are the main ways in Postgres of accessing information in a JSON type. So if I did data and then the single arrow like that, so we'll do the double arrow first into the text of, we saw that before that text was one of those entries in the database. And so text like this from tweets JSONB, and that gives us the actual text right here of the tweet. So not a super interesting tweet, just mentioning a couple other people and then some Unicode here that I don't have the font for. Let's try, so we saw before also, let's go back to our JSON Pretty. So that gave me the text right here. I also wanted to get the screen name, so I have to go inside of user, and then once I'm inside of user, get the screen name of the user. Anytime you're going inside of an object, or let's see, this double arrow sign like this is for finding actual text entries in the JSON object. If you want to get another JSON object, though, you would use a single arrow like this, and then get the user object like that. And then since this right here, this whole thing is a JSON, I can index inside of that with the double arrow to get the screen name like that, and that will give me the screen name. So in general, when you're trying to access information out of the JSON types, the very last, or you'll be using a bunch of these arrows chained together. The very last one of these arrows will always be the double arrow because that will return a string. And then the intermediate ones will be this single arrow, which will return the, or which you pass the intermediate JSON objects to do that. Let's see some possible common error messages here. So if I use the double arrow like this, we'll get no operator matches. Get an error like this, make sure that you're using the single arrows over here and only the last one is the double arrow. If you use the single arrow to the right like this, that's totally okay in terms of you're not going to get an error message. But this right here is still a JSONB object. JSON, if we do PG_type, it'll tell us what's the type of something. PG_type of, there we go. So the type of that is JSONB. If I change this, so as screen _name, and let's add an where clause where screen _name equals JC870 like that. We're not going to get yeah, one of the just copy and paste that over here like that. So here, trying to do the comparison of like this to this in my where clause. This over here is a JSON, this over here is a string, so we can't do any sort of filtering like that. If I want to be able to do filtering, I have to do the double arrow like that. And so it turns out there's only one tweet in this small data set sent by this JC person. Another common thing is that, so one of the downsides of working with JSON data in all languages, SQL included, is that typos are not enforced. There's no type checking on typos. So here, this screen name, we know there's a screen name entry because we looked inside of it and saw it. But maybe I had a typo, and so I know sometimes the E sound is made with an EA instead of an EE. And so maybe I typed in screen name like that, and I hit enter. And it's not going to give us an error message about like the column name is wrong. It's just going to not give us any results because there is no screen name spelled this way. So if you're ever not getting the results that you think you should be getting, very common to have a typo in your list of JSON keys right here. And it's not going to give you an error message when you have a typo. Any questions about the those arrow operators and accessing information inside of a JSON object? Okay, then we're gonna move on to next, looking at how this interacts with the B tree index. So let's say I want to be able to do a search counting all of the number of people who have, or all the number of tweets sent by a particular user. And so doing something like we were doing just this select count star from JSONB, where the screen name is equal to some particular username. This seems like a reasonable query that we might want to run, counting how many tweets users have sent. And if we do an explain on this right now, we'll see that it's using the sequential scan to scan over everything in the data set and do this comparison. And then it does the aggregate at the end to do the count. It's not going to be, so it doesn't take too long on this data set. So let's go ahead and add the timing on and time it. I don't know, it takes about a second. On 100,000 tweets, once we go up to 31 million tweets, that's going to take, I don't know, 300 seconds. So way, way too long for us. And so we need an index to speed this up. In order to make an index on a more complicated condition like this, that's called an expression index, where we're going to not index a column, but index this expression of a column, index this function of a column. So I'll do create index on tweets underscore JSONB. So this is still the name of the table right here. And then in parentheses, I'm not going to have a name of a column. I'm going to have this entire expression right here, like that. And an index like this will let us speed up a query like this. I'm going to hit enter first of all here, and you can see that there is this syntax error. Whenever you have one of these expressions inside of your index condition, you need parentheses around it for weird syntactic reasons like this. You don't need the spaces over here. I'm just adding them to highlight that these outer parentheses are for the create index command here, and these inner parentheses are just to indicate that this entire thing together is one column. Hit enter on that. Takes less than a second to build the index, even less time than it took to run this query up here. And now when we run this query, super fast, and if we explain it, we'll see it's using some type of index scan instead of something else. So creating indexes somehow like this will be an important part of your working on the denormalized data sets, creating these expression indexes. These expression indexes, you could create them on expressions of the normalized data set too. And I do that on a regular basis. I think your take-home quiz will require you to do that at one point, but the assignment does not require expression indexes on the normalized database. Any questions on the expression index? Okay. I want to look at, if we do tweets JSONB like this, it'll tell us down here exactly in our list of indexes what the expressions are that you can search for. And in order to be able to use this index, when you have an operator like equals right here, you must exactly have one of these conditions either to the left or to the right of the equal sign. If we had something that was, say, like lowercasing this, this is no longer, this function right here is no longer exactly matches this up here, and so we'll no longer be able to use the index, and we're back to a sequential scan. Okay, so then back to our JSON operators. So we've talked about the pretty, there's two arrows. These arrows are a Postgres specific way of accessing information inside of the JSON or JSONB types. And there's something generic called a JSON path that works both inside of Postgres and inside of basically every programming language has support for these JSON paths. So we'll talk next about this generic JSON path syntax and how it relates to these syntaxes up here. So let's say, so again, select JSONB Pretty data from tweets underscore JSONB limit 1. So just so we can see what this looks like again. And I'm going to write a JSON path that specifies that this is the particular information that we want. So, and in order to use that, so it's select JSONB underscore, so path query. I always forget exactly what that is. and so I have to look it up, but JSONB path query, then it's a 2-parameter function. The first parameter is the column that you're looking for, and the second parameter is an expression that identifies the location in the JSON object of the information that you're looking for. This expression always begins with a $sign, and the syntax that this expression supports is relatively complicated. So we're going to start with just some very simple examples and build up. But it always starts with a $sign, and then if we say $.user and then .screen name, this user was that first key in the JSON object, and then screen name was the key inside of the user dictionary. And so that's why this gives us the same information as user and then screen name up here. Again, this style of accessing specific only to Postgres. This JSON path right here is supported in every programming language. And so people, let's see, people who only use Postgres tend to use this notation. People who are more polyglots, Postgres, Python, C++, Java programmers, whatever other languages you use, tend to use this sort of notation to access the JSON objects, because it's generic across everything. And then from tweets_JSONB, limit 1 like that, and we get this same value out over here. Let's see. The output of a JSONB path query is technically a JSONB type. So let's do PG_type of like that. So it's technically a JSONB type. If we wanted to convert this to a string so that we can do comparison operations, it's rather obnoxious how we have to do that. We still use this JSONB path query, specify it like this, and then the double arrows like this, followed by a 0. The 0 over here indicating to just convert whatever you had into a string. Don't go inside of a particular key. Enter, and now it's that same information that we had before, but the type will be text. So if you are using only the JSON path style of querying, then this is what you would have to do right here in order to get the text out of a particular key. You still have to add this double arrow with the 0 after it to convert it to a text entry. Any questions about that? Okay. So here, this is very, very simple JSONB, JSON path notation. But JSON paths can be much more complicated than this. This notation right here is not really doing anything that's more advantageous than these built-in Postgres notations. But we'll see some of the features of JSON paths that are really powerful here next. As a quick aside though, so the origin of JSON path is actually, and so JSON path, also sometimes called JSON selector. And the origin of this functionality, JSON path or JSON selector, is that it's to compare to CSS selectors or something called XML path. These are, so CSS selectors used in cascading style sheets. If you take CS40 with me, you use these a lot when you're styling your web pages to identify particular HTML nodes that you wanted to have different styles. XML path, method for searching inside or specifying nodes in an XML document. People realized both of these two things were really awesome, and so they created the JSON path or JSON selector in order to do that. And you'll see both of these two names used interchangeably. And the reason they have these two names is because of these two things having the selector name for CSS and the path name for XML. So yeah, we already saw the Postgres documentation right here. For a full tutorial on this JSON path, JSON selector syntax, this tutorial right here, I think, has a good, like, not just explanation of all of the different features, but like motivations behind it and how they came to be about. So that's a good thing to refer to. Okay, but now into the more complicated uses of the JSON selectors. And in order to introduce these more complicated uses, we're going to come up here to the top window. Again, this top window under week 12. So this is the current assignment. And I'm in my solution right now. So because I'm in the solution, I have this denormalized folder with the solutions inside of there. I'm going to open up SQL.normalized batch 01.SQL. So there's 5 of these problems. We're looking at the first problem right now. This is the normalized version of the problem. Very simple looking query right here. And I'm also going to open up in another tab the denormalized solution here. And we'll work through the solution of this first problem here in class to help you see how to do the other problems. And the first thing that you'll notice is that this solution up here on the denormalized query, much more complicated than for the normalized query over here. And we'll see exactly why that is. But it's related to using these Postgres operators like this in order to do the querying. And we'll see there's some equivalent solutions down here that use JSON path and much simpler to write. So we'll introduce the needed JSON path elements as motivation for how we can simplify this query up here. So yeah, first let's think about what this query is trying to do in the normalized database. The tweet tags table is sort of one of these linking tables that just counts or remembers which tags are associated with which tweets use which tags. And so this query right here is trying to count the tweets, the number of tweets that use the hashtag coronavirus tag somewhere in the tweet. And so let's go back to our JSON Pretty. There we go, JSON Pretty command. And I want to see where in here are the tags stored in this JSON object. And it turns out there's an entities. The entities dictionary contains all of the information about URLs, symbols, hashtags, and other users that get mentioned. Since this first tweet only has users being mentioned, not hashtags, we'll start working with just the users mentions, and then we'll see how that relates to the hashtags afterwards. But I want to write a query that's going to get me the names of the users who are mentioned. Actually, do the screen names of the users who are mentioned in this tweet. So first, we'll write a query that gets me these user mentions. So we'll do data, and then we said there was an entities like that. So let's try that. Okay, so that stripped away everything except the entities. And now inside of here is the user mentions. User, oh, it needs to be in quotes, user mentions, like that. And so there's 2 different user mentions here. At this point, you see that we're no longer, the things inside of user mentions are no longer dictionaries, they are lists. JSON supports either dictionaries or lists as being items or values inside of the JSON object. So in order to access something from a list like this, we could do, say, like that to get the 0th element in the list, and like that to get the first element in the list. In general, though, you're not going to want to use these sort of like number indexing on these arrows. That's sort of like a red herring. Don't go down that path in any of the queries that you're going to be writing. The reason for that is you don't know how many of these entries are going to be in the dictionaries. Some dictionaries could have 0, or some tweets could have 0 mentions of other users, but you could have maybe 50 mentions of other users. And so you don't know in advance what this number is going to be. So you don't want to hard code these numbers. Instead, there's another function that we'll take a look at. This JSONB array elements function. And this function is like the unnest function that we saw with arrays before. So JSONB underscore unnest, like that. And actually, before we call the unnest function here, do this. So get the sort of simplest printing out, or the just printing out the JSON type like this. And in order to make this limit 1 here, I want it to get me just a single tweet, and then get me all of the entities inside of that single tweet. In order to do that, I'm going to change this to use a subquery. So that is going to be my subquery, and say as user mentions right here, name this column as user mentions. And then we'll select from this subquery right here, we'll start with just user mentions like this. So this is the same exact thing as I had before. I've just added the subquery around it, since that'll be useful here. Now when I apply that unnesting function to this, it's going to apply it to the single tweet right here. And so JSONB array elements, we have a single tweet right there. JSONB underscore array elements, like that. There are 2 elements in this array. So even though our limit 1 right here makes it so we get only a single tweet, only a single user mentions object, we'll break that up into multiple using this JSONB array right here. And this, like the unnest function, you don't have to know how big the array is. It's going to automatically do that for you, creating 1 entry for each of the rows down here. And now that I have these JSON B objects down here, I can filter off of those. The result of JSONB array elements is still JSONB. So I can add my my arrow syntax off the end of these, like this, arrow, and then the screen name that we wanted, I think. Yep, and that gives me my screen names like this. Because I really wanted to get it as text, the most correct thing like that would be the 2 arrows right here to give me these as text objects that I can compare with instead of JSONB objects. So these, in order, whenever you have an array in JSON, in order to use this arrow syntax, in order to extract all the information out of the array to do comparisons, you're going to have to use both the arrows and the JSONB array elements together. And that's going to make your queries, I don't know, pretty big and awkward like this. The JSON path, though, for this query is much simpler. So again, select JSONB path query. and then it's the data column. And then the JSON path is the star, then the dot, these two column names right here, entities dot user underscore mentions. And then since this is an array, I can do something like, we'll start with just a 0 right here to get the 0th element, and then another dot to get the text. So this dot text right here corresponding to this, oops, and it's not text, it's screen name. Dot screen name corresponding to this screen name up here, and then this down here corresponding to this section right here. From tweets underscore JSONB, we'll add, we'll just say limit 2. And we get some results like this. Here I wrote limit 2. So we want to get the these two entries right here, which are both being mentioned inside of the first tweet. The second entry down here though is different, because here this 0 says only look at the 0 entry in the array, don't look at all of them. If I change that 0 to a star, that says at this point unnest this array. So look at every entry in the array and apply the screen name to every entry in the array. And now if I do that, then we get these two things right here. So by using this JSON path syntax like this, I don't need to have that separate, separate unnesting call. Any questions about this syntax? That the square bracket index the array, star means get everything inside of it. It's basically the same as unnesting, or the JSONB array elements.
Where is, when you're doing the query right before, where is the context for that output?
This query?
Yeah. And you go to the output, like,
where is this coming from?
Yeah.
Yeah, good question. So the question is that we know where this patch punisher is coming from, because we saw that is actually in this first tweet right here. Here, it's going to, if it doesn't see it in the first tweet, it's going to keep looking on the second tweet and the third tweet and the fourth tweet to find more user mentions until it finds 2 total. So this limit 2 is not looking, it's not limiting to 2 tweets. It's limiting to 2 different screen names returned. So this one comes from the first tweet, and this one comes from the second or third or fourth tweet or something. Yeah, let's do it. So a quick trick in order to identify like which, when you're using JSON like this, in order to identify which are like, so we know at this point that these two mentions come from the same tweet, because we already knew that going into it. But just looking at it, like this, we don't know, this output here doesn't give us any indication of that. And if I did like limit 10 like this, okay, we already know in advance that these two come from the same tweet, but we have no idea like these other ones down here, are they coming from the same tweets or different tweets? A trick in order to figure that out is that, remember there was this CTID system column on every entry in our table and every row in our table. And if we do that, then we can get the actual tuple ID of the corresponding user mention over here. So this now tells us, oh yeah, these two actually came from the same tweet. These two here came from the same tweet. This tweet only had 1 mention. This tweet here had 2 mentions, and so on. So it's, yeah. I would never write like a production query that used this CTID column inside of it. But just for like sort of debugging purposes, orienting myself, that's a good trick to do. Okay, what we're going to do next is see how all of that relates to this, this query up here. But any questions before we basically solve the first homework problem? Okay, so here we're looking at this tweet tags table, and again, filtering on the hashtag coronavirus. The tweet tags table inside of the Python that puts it together looks for tags in two locations, either entities, hashtags, and then text or extended tweet entities, hashtags, text. And again, the result of this right here, extended tweet entities, hashtags, is a list. And so that's why it needs this JSONB array elements right here. Here I'm including the CTID so the actual tuple ID, so that I can do a distinct CTID and hashtag up here. This distinct up here corresponds to this distinct right here in the count. It turns out that for some tweets, the hashtag is listed, it'll be repeated both in this location and in this location down here. And if that's the case, we don't want to count that tweet twice. And so that's why by including the CTID, we can identify that that same hashtag came from the same tweet, and then the distinct will remove it. And then it's just select count star and the where on the hashtag down here. I'm gonna go remove the numbers up here, and let's go ahead and run this. Select count star. Let's see, is there another line? There was. From all of that. And then adding that right there, enter. And we get, so there's 10 tweets in this smaller data set mentioning hashtag coronavirus. And so now let's think of a simpler way in order to write this same query. Simpler way to write this query. And actually, so yeah, two reasons to write this query simpler. One is just that simpler queries are better than non-simple queries. But the other is that this query up here, as it's written, cannot be sped up using indexes. There's no way to speed up this query. And the reason there's no way to speed up this query is because we're using this JSONB array elements function, because we're using this unnest function. This function is called a set returning function. And so a set returning function is a function that can return multiple different rows from the results. And if we try to, we saw before that we can build up expression indexes. The expression in this case that we would want to create an index on, create index on tweets underscore JSONB. And then again, we need the two parentheses like this, the big expression like that. And if we try to do this, hit enter, it'll say error, set returning functions are not allowed in index expressions. So anytime you have a query that includes something, either this function here or unnest, you can't speed that up using indexes. So it's important to rewrite it without this function call in order to be able to use the indexes. And there's a number of different ways to do that. Here is one of them. So here to the left, this data entities hashtags, this right here, gives us that, again, list of hashtags for the tweets. And here we're seeing this double @ operator again. Previously, we saw that for full text search, but this double @ operator can also be used to check conditions on an index. The thing to the left of the double @ operator is always the thing that you're sort of searching, and the thing to the right of the double @ operator is always the condition that you are searching for. Let me write that out. So, thing you are searching at thing query that you're searching for. For full text search, we saw that was TS vector to the left of the @ and then TS query to the right of the @ For JSON, it'll be JSONB to the left of the @ and then a JSONB path to the right of the @ or also JSONB selector. We've seen, so we need to talk a little bit more about more complicated selectors now. We've seen this, this part of the selector syntax so far, that the $, again, indicates sort of the root of your JSONB. So this $, refers to this JSONB over here. This JSON over here to the left is a list and not a dictionary. And so we immediately follow the $, with this right here to say unnest that JSONB and look at all the different entries in it. And then we do the .text off of that. And then in order to make this a condition, we can say, is that text equal to coronavirus? Inside of these JSONB conditions, you need to use a double equals in your condition, and you need to use double quotation marks around whatever it is that you're comparing with, if it's a string. This is different than the normal Postgres conditions, where in a normal Postgres condition, you use a single equals to check for equality, and strings must be contained inside single quotation marks. So again, this syntax right here is not coming from SQL, not coming from Postgres. It's generic for any programming language that has a library for JSON paths, which is every programming language. And so that's why it doesn't follow the normal convention for Postgres. It's following this JSON path standard. And so this thing over here is our query. Again, this thing over here is the thing that we are searching inside of. So this over here, the list of all the hashtags, get the text of the hashtag and check to see if it's equal to coronavirus. Go ahead and run this query. And you see that the answer is also 10, like the longer query that we had up above. So it's much smaller query, much easier to read once you get the hang of it. And also we'll be able to index this query because there's no set operator anywhere inside of here. There's just this double @ sign, which we'll talk about how to make indexes for next. We previously saw creating an expression index with a B tree on a JSONB type to index the user.screen name. And here we could use a B tree. We did not need these double @ signs, did not need these JSON path queries, because this type right here nowhere did not use any arrays anywhere. Because that did not use any arrays in the JSON. User and screen name, both dictionaries, no lists, no arrays, no square brackets. Here, the hashtags does use a list, does use the square brackets. So we need some sort of way to look at every element in the square brackets. And so you're going to have to use this @ syntax. Must use the @ syntax for entries in JSONB with arrays. That @ syntax will be using a gin index, which we'll talk about here in a minute. And in particular, cannot use a B tree index for something like this to speed it up. Any questions about? Yes.
Could you go over again what the asterisk in the square bracket means?
What this in the square bracket means?
Yeah.
Good question. So the question is, we have the square brackets, and what exactly is the star doing inside the square brackets? And let's come back up to this query right here to see what the star is doing. Anytime you have, and let's see, I'm going to come back to that. Yeah, I guess JSONB underscore pretty, like that. So here the user mentions has changed to which users, which TIDs are getting mentioned, because there's no order by clause. So Postgres is free to select whichever results it wants. So it's a different tuples that are getting returned now. But we can see that here when we do the .user mentions, maybe let's make this bigger until we get, okay, so number 7 has some information inside of it here. And all of these are lists, arrays in JSON terminology, but they're not dictionaries. And so in order to get a particular entry of a dictionary, we could do like index at 0 like this, and that'll give us the very, the 0th entry, the first entry. But in order to get all of the entries, we would do a star like this, and that gives us not just the 0 position, but all of the positions in the array. So that's, if we had a larger array, something like that. Again, the way to think about the square bracket is, or the way to think about the square bracket star is it is equivalent to using this unnest function, JSONB array elements, unnesting that type, and so that we can use every element inside of this array. The disadvantages of using this unnesting function right here are that you'll have to write out explicit subqueries, really large queries, and you won't be able to index that. Let's see, because Postgres reordered the entries here that it's returning, these results I don't think are super informative, so I'm going to change we'll see something a little bit new. Rather than using a data column, I'm going to explicitly provide some entries here. So I'm going to do, let's see, 1, 2, 3, 4, 5, like that. Type JSONB. So this is just a JSONB object right here. And maybe let's actually use text values. So this is a test like that. We have just a list of strings like this, and I want to index this list of strings. JSONB underscore path underscore query. The first element of this function should be a JSONB object. This one here. The second element should be a JSONB path, something like this. And so we'll start with just a $sign like that. That gives me the JSON object exactly as it is. If I do a 0 right here, that gives me the position 0 in the array, a 1 here, position 1 in the array, 2, and so on. If I put a star right here, it unnests that array, giving me each one of those elements as its own particular row. So this right here, equivalent to JSONB array elements. Like that. So anytime you see a path that contains the square bracket star like this, that's equivalent to calling JSONB array elements on whatever's to the left of the square bracket star. Yeah, this is getting used to the JSON path syntax is definitely a little bit confusing, and can just take some time playing around with it and trying out different things. And it's very common, even for me now, to be a little bit surprised at what a JSON path does. So I always test them out, making sure that it's giving me something reasonable before like sticking it into a production thing or sticking it into the large database that might take an hour or so to run. Does that answer your question? Any other questions? Okay, so then on to making indexes for this double at operator. The name of this index is called a gen index, stands for generalized inverted index. In this link over here, it has this little note at the top inside of the README file. So again, a lot of Postgres' documentation is buried actually in the source code in the README file. And it specifically says right here that gen stands for generalized inverted index, and you should think of it like a genie because it's magical and not like a drink. We're going to see later there's an extension to the gen index called the rum index. The gen index created by this company that's now defunct, doesn't exist anymore. Go to that link, doesn't exist. One of the nice things about open source is even though that company doesn't exist anymore, their contributions to the world still usable. But the rum index created by this group of Russians, and Russians like their alcohol, so they decided that gin should actually stand for drinks, and so that's why they called their extension to gin rum. Just following along the alcohol naming convention. But the idea of a gen index when you're using full text search. So this is again that same link to that Russian Haber website. Here they have a table up here. So we have this a doc, which is text, and then a TSV is a common shorthand for TS vector. And they're inserting all of these values right here into, so just a bunch of sentences into the documents. And then this update condition down here just says that the doc underscore TSV column should be equal to calling to TS vector on doc. And again, they're not specifying a language here in to TS vector, but English is going to be the assumption. And this syntax for creating a gen index, when you're creating a gen index, the thing inside of it should be either a TS vector or a JSONB object. And the notation, the thing that's different, is that we have this using gen expression right here between the name of your table and the name of the column that you're indexing. Or alternatively, this could be an expression. They could have put the to TS vector right here inside of here. But to try to simplify this command right here, they made it as two separate steps. But again, the key thing right here that's new is this using and then the name of the index type that you want to use. So using gen. This gen index, the way it's structured is that there's internally a B tree, and this B tree stores all of the information in this B tree is all of the words in your document. And in particular, the words in the document as they're represented by this TS vector. So up here, you can see there's a lot of these stop words like a or am, I. Those words not represented down here in the B tree. You can see there's, here are the words in the B tree. And then with these numbers down here, they represent the tuple IDs of every tuple that contains this particular word. So the word slit has many different tuple IDs associated with it. If we come up here, the word slit appears in many places. So like slitter right here, after it's stemmed, we get just slit like that. And then I think maybe every one of these sentences contains that word, and so there's many tuple IDs associated with slit. The word good only has one tuple ID associated with it. These black lists of tuple IDs are called posting lists. If there's a very small number of tuple IDs associated with a particular word, it's internally just going to be stored as a linked list, and so it's called a posting list. Posting just means it's the list of tuple IDs. But if there's a very, very large number of these tuple IDs, they will also be internally stored as a B tree. And this ensures that those tuple IDs can be easily stored in a sorted order, so that when you do a bitmap scan, you'll get the tuple IDs back in a sorted order, which is what's needed for a bitmap scan. This picture right here is sort of the main picture to try to understand for the B tree index, in combination with this picture right here. So the first picture just shows the structure of the B tree. The second picture over here shows the what happens when you do an actual query on the B tree. So here is the query that they're doing. This query is looking for the word many and the word sitter, so looking for sentences that contain both of these words. Again, the full TS query syntax, I think when you see it, it should be like pretty obvious what's going on, but writing them out, you'd have to refer to the documentation to see all the different features. So it's looking for sentences that contain both the word many and the word slitter. And then it looks inside of here for MANI is the stemmed version of many. And there we go, right here. And then slitter over here finds these two lists of tuple IDs corresponding to those two words. And then in order to do the AND part of the TS query, it's going to take the bitwise AND of these two tuple IDs, and the only thing in common with them is the tuple ID 0, 2, and so we get 0, 2. Yeah, there's not too much time left in class, so I'm gonna jump ahead real quick, and I'll just real quick show you how to create a GIN index, which will speed up this query here, and then we'll be done for today. So this index, or this query again, is taken, I don't know, a while to run. If we do the explain on it, you see that everything is the sequential scan on this particular table. And so in order to speed up this at operator, the thing that's to the left of the at operator is what needs to be inside of the query. Sorry, inside of the index. So it'll be create index on the name of the table, tweets underscore JSONB, then the using GIN, like that, and then inside of my expression index, like that. And this will be used to speed up this operation right here. And then I need a second one in order to speed up that second operation. That second one has extended tweet, extended underscore tweet, like that. Enter. And now when I explain this query up here, we can see that it is using an index scan on those, sorry, a bitmap scan on those indexes. So that's the way that you will speed up your queries, whether they are full text queries or these queries into JSON that have to use the @ signs. Just create your index, GIN index on the thing that's to the left of the @ signs. See a little bit more about this on class on Friday, but at this point we've covered everything that you need for the assignment. So I will, yeah. Any questions about anything? Question? Steve?
I'm not sure I missed this, but if we look at the structure, I was wondering how is it determined, like what's at the top? Like, I guess I kind of
Yeah, so the question is, We have some different words up here, some different words down here. How is it determined, like which words are up here and which are down here? The structure of this tree up here is the same as the structure of a B tree. And so it has this, this sort of search property that any of the words up here, if you go left, they'll all be less than. So all of these words right here, less than Manny, less than or equal to. All of these words in the middle, between Manny and Sleekest, and all of these words on the right, greater than whoever. So it just maintains the same structure as the B tree. The difference between the GIN index and the B tree is that the B tree doesn't break up the text in any way. It just uses exactly, when you're using a B tree on this, it uses exactly what is in here as the entries inside the B tree. When you're using a GIN index, it breaks up this into whatever its components are. So the TS vector would be the individual words rather than the entire string, and that's where these words come from. Did that answer your question? Okay, then I'm happy to answer any other questions that people have, but that's end of class for today, and see you on Friday.